Google have released Gemma 3, their latest open weights series of models, and the largest of those models, which still fits on a single GPU, has gotten into the top 10 on Chatbot Arena. Chatbot Arena involves having humans compare blind the performance of different LLMs, and they give their preference. And you can see here that Gemma 3 27B is up there with O1, Gemini 2 Flash, DeepSeek, ChatGPT 4o. It's up there in the top 10 with all of the models. So in this video, I'm going to take a look through the technical paper and I'll compare some of the benchmark performance of this Gemma 3 model against others like Quinn VL and DeepSeek V3. Let's take a look at the paper. So we'll work down from top to bottom here, noting first of all, as I said before, that the 1B model has not got a vision encoder, whereas all three other models have got the same vision encoder. So keep that in mind when we look later at the results comparing 4B to 27B, because they just have the same vision encoder, but different size text transformer models here. Now, Gemma uses a traditional model architecture. It's a transformer model that includes attention. One of the key differences is that in each of the layers, there is not a full global attention. There's not the use of full global attention whereby a token looks back at all previous tokens. Rather, in every 4 out of 5 layers, each token will only look back at about 1,000 previous tokens. This is called a sliding window approach, and it's a mix of using this local sliding window for 4 layers, and then using full global attention, and then using 4 more local layers, and then full. And by doing this, you save by a factor of about 5 in the amount of attention calculations, and you save a factor of 5 in the size of your KV cache. So you're going to be able to fit longer context questions, longer context queries on the same GPU without running out of cache space or VRAM as easily. Other than that, there's a vision model included, as I mentioned, and the Gemma 3 models can support a context length of about 128K tokens, which is similar to the Llama 3 series of models. Now, these models were trained on TPUs. Google tends to train on its own hardware rather than using NVIDIA. You can see it's using V5E and V5P type TPUs. The latest TPU is actually V6E. I think E tends to be the smaller and P tends to be the more performant for a given class. So 5E would be a bit less advanced in terms of performance and throughput than 5P. And in the 6 series, there's currently just the E that has been released. And this is not used for the Gemma 3 models. I assume it's probably just being used for the Gemini models, which are the private gated models. You can see actually a V4 is being used here in the case of 12B. So possibly for reasons of availability of TPUs, or maybe for doing some comparative work, they used the V4 TPU right here. Now, the models are available in BF16 format. This is BrainFloat 16. Of course, that's not supported in Collab, so you have to run in Float 16. Very common to release models in 16-bit, although DeepSeek has kind of changed that and released its models lately in 8 bits. In fact, not just released it in 8 bits, actually trained in 8 bits. So these models still are using the, you could call it, old approach of training in 16 bits, but they do release quantized versions in 4 bits and also release an FP8, which is an 8-bit version that probably has very good quality, but allows you to save on VRAM by a factor of 2. Here you can see if you load the BF16 model, it takes 54 gigabytes. And then if you have 32,000 tokens of context, it will take an additional 72. So that means you would need a total of over 136 gigabytes of VRAM to run a 32 size query on a GPU that is, sorry, let me say that again. It will take you 54 gigabytes for loading the model and then 72.7 for the KV cache. Whereas because of quantizing this down to 8 bits, you're able to bring it to 27.4 and then 46.1. And note that this would be a lot larger. So these numbers for KV cache would be a lot larger if you had to use attention in every single layer. And because attention is just in one of every 5 layers, this is effectively reduced by a factor of 5 compared to what it would otherwise be. Let's take a look now at the pre-training. This is the part of training where the largest amount of tokens is used. 14 trillion used for Gemma 27B, 12 trillion used for 12B, so not that much difference there. but quite a bit less for the 4B model, just 4 trillion tokens, and 2 trillion tokens for the 1B model here. Now, the tokenizer that's being used is very large. It's got 262,000 tokens. I think the Llama 3 series has got 120, which at the time was a very large tokenizer. So there seems to be a trend towards using larger and larger tokenizers, which definitely supports, which better supports using multiple languages other than just English, but seems to generally give performance improvements as well. Now, there's something important here in the overall training, which is distillation. So the Gemma teams have decided to first do pre-training and then do distillation. And this distillation means taking the knowledge from even stronger models and distilling it down onto this Gemma 3 series of models. Now, we don't know which teacher models are being used. We might speculate that they could be Gemini Flash 2.0, or possibly Gemini Pro 2.0 or Gemini Pro 1.5. Now, the performance of these Gemma 2 models does in some cases exceed the Flash 1.5 and even match Pro 1.5. So you might expect distillation was done rather by the 2 series because the teacher will generally still remain stronger than the student models. Now, after pre-training and distillation, there's then a period of instruction tuning, which will align the model and improve performance. There's reinforcement learning that's been done through these bond, warm and warp techniques. I haven't dug into those, but there's also reinforcement learning being done on a few different types of data: human feedback data, code execution feedback, and then ground truth rewards for solving maths problems. So here involving quantitative data, filtering or reinforcement learning on the correct answers and using that to improve performance. And the reasoning performance and maths performance is very strong of the Gemma 3 models. Moving on to the table here, this is the chatbot arena table at the time of publication. You can see Gemma making it into the top 10 or to the joint 9th, up there with O1 Preview, O3 Mini High. And it's a significant improvement here on Gemma 2, which was the previous generation of this model here. Now, when it comes to benchmarks, this table shows the performance on a combination of text and also reasoning and then vision type benchmarks. MMMU is a multimodal benchmark. And this table nicely shows you how the Gemma 3 model compares not just to Gemma 2, which it improves significantly on, but also to the series of Gemini models. And you can see that the Gemma 3 family, in a lot of cases, it's able to beat the Gemini 1.5 Flash model. So here for MMLU Pro, it's at 67.5, just a little ahead of 67.3. GPTQ Diamond, it's a little bit weaker. On maths, it's actually stronger. And on MMMU, which is multimodal, it's actually stronger than the 1.5 Flash. Now, when you compare it to Gemini 2.0, the Flash model here, for example, generally Gemma 3 is going to be weaker. And you can see, for example, it's particularly weak on the simple QA test. I'm not sure exactly why the Gemma 3 model is weaker on this, but the Gemini 2 series of models is significantly better here. Now, the nice thing is that all of these comparisons are done by Google, so they're apples to apples in the sense that they would have used the same prompts, the same number of shots, the same number of samples. So it probably is a very good like-for-like comparison when we compare Gemma 3 with the other models that are shown here. What's more difficult is to compare Gemma 3 with, say, Quinn models or DeepSeek, although I will do it because often the testing can be done at slightly different settings for few-shot examples, and this means that it's not necessarily apples to apples. But we'll come back to that a little bit later. There are some ablations that are being done comparing different design choices that could have been taken. Here, for example, is the choice of how often to do global attention. Do it every layer, do it every 3 layers, every 5 layers, every 7 layers. And basically, the team finds that there's not all that much difference. You can go out as far as at least maybe doing it every 7 layers and not see much performance or perplexity degradation. There's also an ablation done on the size of sliding window in the local layers. And you can see here the perplexity also not significantly impacted if you go down as far as a sliding window of 1,000 tokens, although it does get a bit impacted here, at least on the 2 billion parameter model, when you are using attention only 1 every 3 layers and you go down to the 512 sized window. This here is a graph showing you the memory savings, comparing in red the memory required if you've got the attention being global only every 5 layers versus every 1 layer. And yeah, you have a roughly factor of 5 saving in your KV cache, which lets you handle many more sequences or longer sequences within the same GPU. Here on the right hand side, you can see the long context. So you've got the perplexity, lower is better, versus context length of the different models. Blue is 4B, orange is 12B, and green is 27B. And what it's showing is the difference between the dashed line, where there's pre-training, there's no training for longer context, and the solid line, where there is training on longer context sequences. So this is done in 2 phases. The model, I think, is first trained on 32K sequence lengths or lengths going up to that. And then its context is extended with a second phase of training towards the end. And you can see that when this second phase is done, the solid line ends up lower than the dashed lines, indicating that the context extension is working. Now, interestingly, in the case of the 4B model, there's kind of a soft runoff here of the context of the perplexity, whereas there's a very sharp increase in the 12B model when you get to 32K context. And again, then at the 27B, it's kind of smooth. So that strikes me as quite an unusual pattern for the middle-sized model. And I don't have a clear explanation, but something different appears to be happening with respect to long context in this 12B model here. Now, we don't know exactly how many tokens are used for the distillation phase. So there's pre-training done on either 14 trillion, 12, then 4 or 2, depending on the model size. And then there's a period of distillation. It's not disclosed how many tokens are used. Typically, it's about 1 to 2% or 3% of the original training set. And what's been shown, though, here is an ablation, although it's probably an ablation on one of the smaller models, maybe the 2B model. Sorry, the 1B or the 4B, I'm not sure. And what's happening is it's showing a comparison between distilling from a very large teacher or a somewhat large teacher. And what this shows is when you are at a small amount of distillation tokens, you do better by using a smaller teacher, probably because it provides regularization. And when you have a very large amount of tokens, or relatively large amount, when you're doing distillation, that means you should prefer using the strongest teacher possible. Now, when it says small versus large, I assume both of these are actually still quite large, although I'm not sure. For example, this ablation could have been run on the 1 billion model as student and then using the 12 and the 27 as the teacher, or it could have been run using, say, Flash and Pro as the teacher. So it's a bit unclear here, A, how many tokens are used for distillation, and which models are used for distillation. Furthermore, it's a bit unclear why all the pre-training was done and then distillation was done. You would think for the weaker models, it might have been possible to, for example, initialize from Gemma 2 and then do distillation, or at least cut a lot shorter the pre-training if there was going to be a phase of distillation done. But maybe there are some findings that actually doing the pre-training is important, and the best results are from doing normal pre-training and then boosting performance with the distillation, which is exactly what has been done in this paper here. Something interesting that's not often reported in these papers is the regurgitation rate. It's called memorization, but I think it's clearer to think of it as regurgitation. It means when you ask the model a question, will it regurgitate its raw training data much? And the answer is this is very, very rare. In fact, it's become increasingly rare. With Gemma 2, the exact regurgitation was about 0.01%, whereas now it's down below 0.001. Now, as to why this regurgitation rate is decreasing, I'm not sure. Possibly just more post-training with reinforcement learning is throwing the model distributions away from having exact patterns in the original data. I suppose the further you do training after your pre-training, the more your distributions will move from that pre-training data, and so you'll have less regurgitation. And I assume this is measuring regurgitation of the pre-training corpus as opposed to that of the post-training. So maybe that's a distinction that would be interesting to dig in on, or perhaps the team has, but it's not exactly shown here. Now, I will go through the results and compare them with other models, but before doing that, just a quick note that Gemini Google do a good job disclosing exactly how they run each of the tests. So for example, GPQA, it's run using 5 shots and using chain of thought. And this is useful information because it allows us to then determine if we're doing apples per apples. Unfortunately, this kind of information is not in every report. For example, I can't find it in the Quinn 2.5 VL report, which makes it difficult for me to say exactly when we're comparing the numbers across the models. So with that, as a quick overview of the paper, we will take a look at some of the results, comparing Gemma to Quinn and comparing to DeepSeek. I've pulled together here just by reading the papers and pulling out some of the comparisons. By the way, I tried doing this with by using AI, and it's quite a difficult task asking AI to compare across documents multiple metrics. So I had to read it myself to be sure that what I'm saying is directly from the paper. And there are two things I want to compare. First of all, I'll just comment on the performance of the pre-trained Gemma model and then the instruction-tuned model. So PT is pre-trained and IT is instruction-tuned. And then I'll comment on comparison of the Gemma performance with the Quinn VL model and also actually DeepSeek R1. So the performance improves when you instruction-tune Gemma. For example, the maths performance in zero shot improves very significantly from 50 up to 89. GPQA, it goes from 24 up to 42. The document performance, this is Doc VQA. It's about reasoning through the text of documents. And that performance only increases a little bit. And the MMMU, which is a multimodal benchmark, that improves, I suppose, significantly by 10 percentage points here. So you can see that by instruction tuning, there are some significant improvements in performance, although the performance improvements in the Doc VQA are not so significant. Now, something I should have shown you back here on the paper is the performance in the visual tasks. And what you'll notice here when you look at document performance is that actually the three models, even though different in size significantly, the Doc VQA performance does not change all that much. For example, the 12B and 27B are only 3 percentage points apart on Doc VQA. Now, the difference is larger in MMMU. Perhaps that's because MMMU depends more on the reasoning capabilities of the LLM part of the model. And so you see a larger difference between the 4B and the 24 and the 27B model. By comparison, if you take a look at some metrics just around text performance, not visual, you'll pretty generally see a large difference between the 4B model and the 27B model. So yeah, the differences are smaller in the model sizes for visual, and that's partly because the vision encoder is the same in all three of the models, despite the models otherwise being different in size. Now, when you're thinking about open source performance, one of the first things to consider is how does a model compare to Quinn? Because Quinn generally have very strong models and their vision models are among the strongest. So I've taken out four metrics to compare performance between Gemma 3 and Quinn 2.5 VL. The maths comparison for a numerical capability. Here you can see Gemma is a little bit stronger at 89 versus 83. And I know for sure both of those are evaluated on a zero-shot basis. Now, DeepSeek R1, by comparison, is even stronger. It's a reasoning model, so that's perhaps not surprising. On GPQA Diamond, which is a more general form of reasoning capabilities, graduate level, Gemma 3 is at 42, Quinn is at 49. So Quinn here appears to be a little stronger, but DeepSeek seems to be even still much, much stronger. On the vision benchmarks like Doc VQA and then MMMU, which is multimodal reasoning, you can see that Quinn 2.5 VL is stronger on Doc VQA and is weaker on the MMMU. Now, I'll note here that I'm not entirely sure how many shots are being used for the Quinn 2.5 VL. You can see there are multiple shots being used for all three of these on Gemma, and that is disclosed clearly, which is good in the paper, but it's hard for me still to compare directly with Quinn. So on these metrics here, it seems like Gemma 3 is maybe in the ballpark of Quinn 2.5 VL. I wouldn't be surprised if you see cases where Quinn VL is a bit stronger, but maybe there are cases too where the Gemma 3 model is stronger as well. Now, I do plan to make a follow-up video where I'll cover in more detail the inference and fine-tuning and even reinforcement learning of these models. But for now, just a few tips on the status at the time of recording. You can download the models from Hugging Face. There's the Gemma 1B model, the Gemma 4B, 12B, 27B. If you're using the 1B, note that you will want to load it using Gemma 3 for causal LM if you're using transformers, whereas the 4B and larger models, you need to load with Gemma 3 for conditional generation. Now, I have started a Collab notebook I'm able to run the Gemma 1B model. I'll share a link to this in the description below, but I'm having issues with seeing any outputs on the larger models and hope to resolve those issues fairly soon. If you want to inference, typically you would go to something like VLLM or to SGLang, and you can see that Gemma 3 is actually supported by VLLM, but you need to build the libraries from source, which is a bit inconvenient. Later this week, though, it should be part of the latest release, and I'll put up a one-click template for being able to inference the VLLM model and also SGLang, which I expect will support Gemma as well. Now, in terms of fine-tuning, before you can think about fine-tuning, you want to be able to properly load the models and make sure you're understanding the tokenization and the chat template formats. I'm not at the point where I've got that working just yet, as I mentioned on the Collab notebook, but once I do, I'll update the advanced fine-tuning notebooks, and I'll also go through a reinforcement learning type approach for tuning the Gemma models. What is particularly interesting about the 27B model, because it performs similarly to, in some ways, the DeepSeek V3 model, but it can fit on a single GPU, is that it opens up doing reinforcement learning on a single GPU. It's very difficult to do that on DeepSeek because the GPUs required are so many. But the fact that we can now do reinforcement learning on one GPU with a very strong base model, which is critical to getting good reinforcement learning performance, that potentially opens up a lot more capabilities for doing open source type improvements through that RL type process. And that, folks, is it on my initial review of Gemma 3. If you have any questions, let me know in the comments. Cheers.